Good afternoon, students. So, welcome to our online session. In today's sessions, we are going to continue the same concept of our laser. In the previous session, also we talk about lasing action. It consists of two stages, stage one and stage two. What is the stage one is all about? We are going to take the forward one kind of thing, right? We are just taking the first end of it when we just want to find the analysis. We can do it by using the two stages. One is stage one and stage two. We already discussed about these two concepts. We have seen the threshold condition, how the threshold condition can vary, and what are the parameters that the threshold condition is going to depends. That also we have learned in the previous session as well. In today's sessions, mostly we are going to concern about their stage 2, right? Stage 2 also we covered. What is the stage 2? Try to get that it is going to make one side as a reflective, other side is a transparent, just to emit the light out, right? For that particular reason, we just want to say that the stage 2 will be going to consider only those wavelengths sustained for which round tip phase of reflected light is same as a forward light. So the kind of delays, whatever the rest of the part is there apart from the kind of light is transmitted, that will be considered to be the decay, right? That is also we covered in the previous topics as well. So now in the further clarification, what we have learned, we have seen the lasing action as well, right? So what is the lasing action is all about? One end should be the input and other end has to work as an output P of L. Here's the input and P of 0. This also we covered, and we come to know that it can work in a two kind of thing. One is the active medium. So when we pass that particular light towards the one end, we just want to see how the lasing action is going to work. So basically, length of the cavity 1. What is the first input we are seeing? The cavity. If you want to see that to choose given to the choose the wavelength, it is going to gain one end, another end should get the losing part. So if it's getting that kind of thing, if the one end is becoming the gaining end, another is becoming the losing end, if both the things is going to be considered, then it is considered to be the lasing action is going to take place. How we get the overall gain of it? Your gain can be obtained by taking the total gain should be greater than the total loss, right? So whatever the gain we are considering, that should have the more number of total gain elements that should be there when compared to the total loss, right? The light increases due to the stimulant emissions because laser is going to take the stimulant emission. If at all you do have a spontaneous emission, that could be taken care first thing, then later on it will move to the stimulant emission. Clear? The next thing what we are going to see is about the lasing action, how it is going to take place. So basically, optical power P would always vary with respect to exponential factor with the distance Z, right? So in that, if you want to differentiate that particular thing, if you want to find the power of the optical power, how do we get that? P of Z is equals to P of 0 e power minus alpha bar of Z. What is this exponential factor of that alpha bar? Alpha bar if we consider to be the effective absorption coefficient of the material. And then P of Z we can write as P of 0 into exponential factor e power minus alpha bar of Z. By solving this, if you differentiate dP by dz, what we will get? E power, as it is the same factor, we can write it as alpha bar, right? We want to get the alpha bar. How do we get dP by dz? Differentiating with respect to z. What will get? We only get this P of 0, right? So P of 0 will become, we are writing this in initial value, and if you want to write the alpha bar from this particular coefficient, we can get it as minus 1 by P into dz by dP by dz. Okay, we will get the P value. We were shifting this P on right side. P of 0 we are writing as P. So we are differentiating dP by dz, and inside if you shift inner derivative of this will be Z is 1, right? So minus alpha bar you'll get. So what is this minus alpha bar? We are keeping minus alpha bar, we are writing as it is, and then we just want to substitute. What is alpha bar is over here? It is the effective absorption coefficient of the material. Next thing, we want to find how much is the beam, right? Because we know that the laser can pass a single beam of light, right? It's a mono. In that one, how do we get that? How much is the beam that is supplemented due to the stimulant emissions as it transfers, that can cause a gain, right? As we talk about the gain, one end needs to be gained, other end needs to be lost, right? So how do we get that gain? P of Z. So P of Z can be obtained by using the same formula, P of 0 exponential G bar of Z. We are using some other factor. Here is the positive, here is the negative. Clear? So one is becoming losing, another is becoming gain. So I want to find how much the gain. Same here, alpha bar is 1 minus 1 by P. Here we have positive, right? Plus. So that's the reason here we do have only 1 by P dz by dP. So this factor we have wrote over there. After writing that thing, what is the next thing? If you combine both things, like if you combine this and this, what I'm going to write? P of 0, this as it is. Now alpha bar and G I'm writing as common because both are exponential only, right? The bases are equal, power should be added. E power minus alpha bar of Z, E power G bar of Z. The bases are equal, A power M into A power N, A power M plus N. So that's what? E power G bar minus alpha bar of Z. We get this P of Z because P of Z both the things are common, right? So per round trip, whatever is the round trip we do have, if you want to write Z, we know that from the formula, right? Z is equals to twice the length. If you want to find how much is the length of that one, if you substitute that, what you'll get? Wherever z is there, write 2l. Wherever z is there, we wrote 2l. So if you want to find the further clarification of it, how it is going to work on it, how do we get for oscillation to get the sustainability? We know R1 R2 P of 2L always greater than or equals to initial condition. Obviously, when we see the initial condition, when we see the kind of light it is going to take it, that always should be greater than that particular formula. If you shift this is in denominator, if nothing is there means 1 will be there. So this is R1 is the first cavity for that reflecting end, and R2 is the second cavity. We have already seen from the graph, and P of Z we are replacing by 2L, right? So that is greater than or equals to 1. So that always must be greater than 1. That means solving for the limiting condition means what is the lower limit and upper limit. If you want to find the limiting factors for that particular condition, how do we obtain it? We can obtain by using R and R2. This is what is the formula of this P of Z, 2L into P of 0. It's nothing but e power, right? We already formed just now. G bar, this is for gain, this is alpha bar is for loss. So 2L is equals to, suppose we are equating with 1. So e power, e exponential factor, if I keep on right side, it will become log. So this in cross multiply this 1 by R1 R2 will left here. E factor I want to remove it. So E will become log of 1 by R1 and R2 minus alpha will become plus alpha, and 1 by 12 will be as it is. This is just to simplify. How I'm simplifying? I'm just shifting R1 and R2 on right side. So it will become 1 by R1 and R2. I have e power g bar minus alpha bar into 2n, right? So E, if you shift here exponential, it will become log. So log of 1 by R1 R2. What left here? G bar minus alpha bar into 2L. Into 2L shift this, it will be divided by 2L. Minus alpha bar you shift on right side, it will become plus alpha bar. So we substituted those all kind of thing, and we got G bar, gain formula. If R1 and R2 both are equals to R, what I can write? R and R gets cancelled, right? Here, what I can write for this R1 and R2? R1 and R whole square I can write. This 2 will come here. Log x for m is m log x. So how I will write this? This will become 2 and 2 cancel. Only will get 1 by L log of 1 by R. This is the expression for finding the gain. Clear? This is the Lazing action. How the Lazing action is going to get the oscillation. Oscillation condition is this, and the limiting condition is this. So when we take oscillation and limitation both into consideration, we can able to write that particular form of this gain as it is. Next thing, what is the relation between the threshold current and threshold gain coefficient GTH? We have to find the relation, right? Because we should know that when we see the threshold current, it is what we have seen dP and d alpha, right? So what is the current di and dP? That we need to see. So we are assuming one factor, threshold current density JTH for simulated emission is proportional to the threshold gain coefficient. So gain of that particular will be beta bar into JTH. Density into beta is equals to your gain, right? So we know that GTH, right? What is the GTH? We just now find the expression for it. So this value shift this side, it will be divided. We got density. Again, the same R1 and R2 are equal. So R and R will be R square. 1 by R square is R power minus 2. Minus 2 will shift here, it will be 2 by 2. This 2 to cancel. Alpha bar here should be my negative. Negative value we are not writing because we are writing as 1 by R only. If you wrote R, we can write as minus here because log x for m is m log x. So this has become the density, right? We obtain the density for the threshold current and the threshold gain coefficient for the given laser component. So we obtain both the things into the consideration whenever we want to find their analysis. This is how their analysis can be able to obtain. Next thing, what is the reflectivity for normal incident of a plane wave on semiconductors? If you see how much is the reflection is going to be there for the normal incident. Since the light is getting incident towards that, how much is the part we are going to get that? On what basis that light is going to take that part? All the things we should know it, right? So in order to get that everything, we just use this relation. R1 is equals to R2 is equals to n minus 1. What is this n actually? The air layer is 1n. 1n is a refractive index we are considering by using the Fresnel law. N is nothing but refractive index, right? Air layer interface can be obtained by using the Fresnel law, which is given by this formula. R is equals to R1 is equals to R2 is equals to n minus 1 whole square by n plus 1 whole square. So where n is actually what? Refractive index of semiconductor material. Okay, so that is considered to be the gallium arsenic. So we can write ITH is equals to, what is the density? What is the current? Is nothing but, basically what is density actually? Density is nothing but current by area. So if you want to find current is equals to JTH, density into area. Clear? Area of the optical cavity. Here we are assuming as an optical cavity. That's the reason we are mentioning here as an optical part. Clear? So this is the formula to find the threshold current. How much the threshold current is going to obtain in our medium. Clear? Next thing, how we get the external differential quantum efficiency. Our main concept is efficiency, right? How much is the efficiency? We are going to get that. That can be expressed in many ways. One of the ways is what? Finding the number of photons that is emitted per radiative electron hole pair that is going to be recombined by using the above threshold. What is that? Efficiency of external part for that differential quantum efficiency given by eta of I into gain minus alpha bar by GTH, right? We know that output by input is nothing but efficiency. Same thing, here also we are applying the same formula. External is nothing but efficiency of the internal quantum efficiency into output, that is gain minus loss. Loss we can assume as alpha bar by gain. What is eta I? Internal quantum efficiency. How we obtain that one? That is given by number of photon produced in the laser cavity to the number of injected electrons. If you divide both the things into that particular formula, we can able to find eta of I. So eta of I, if you substitute, we already found this GTH, right? So that GTH and everything we are replacing, we are just substituting and we can find what? The eta of external. Next thing, what we have to see how much is the external it efficiency, that is given by internal efficiency of quantum into 1 by, what is this actually? This is nothing but the GTH formula, right? That GTH we are writing. In the upper side, GTH and alpha we just shifted in denominator. That's what this at the end we receive as eta of external is equals to eta of internal into 1 by 1 plus 2 alpha bar of L by log. This is natural log we can write, or log also you can write. So by substituting this value in that equation, we get the what? External differential quantum efficiency, right? So we obtain that external efficiency of that one by taking the differential quantum, by providing the some sort of external part of it, right? So this also we obtain. Next thing, we have to see how much is the external differential quantum efficiency can be expressed in terms of the kind of portion of the curve for the power that is going to emitted with respect to P, right? P versus current I. How do we get that? So this is given by that another formula. External efficiency is equals to Q by Eg. What is this Eg actually? It's nothing but the gap, right? Normally we'll say Fermi energy gap, but here we are having the gap between the cavities. So that's what Q is nothing but charge by Eg into dP by di. So P is the power, I is the what? Current. The current what we are assuming for the threshold. So Eg is what? Band gap energy of HF or electron volts. So what is Q? Q is nothing but the charge on electrons. How much is the charge is there on the electrons? If you want to consider that as well. So that's how we can obtain your external differential quantum efficiency. That is also going to use by considering this given parameter, right? So the main parameter is about how we find the external efficiency for differential part of it, that we can obtain by using both the relations. First relation, the previous one what we take for G bar, GTH and alpha bar, that also we can replace, and for this end also we can write it down. For the both the ways we can write that external differential quantum efficiency, right? So we need to understand how the quantum efficiency is going to use that. That is most important part that we are going to design in this particular part of it. That is the external differential quantum efficiency, that is given by Q by Eg. What exactly we are finding? We are finding the experimentally the eta of external can be calculated from straight portion of curve for emitted power P versus current I. How we get that? So by using that relation we can use it. So if you have this both the things into consideration, we can able to find total efficiency, right? Total means output photon, total number of output photon by how much we are giving the input, that is called it as injected electrons. If you take both the things into consideration, then only we can able to find out the total number of electrons that we are going to get from this particular efficiency, right? So that's how we are obtaining that particular relation. Next thing, we know that what is the formula of total photons? P by I. What is the injection part of it? Eg. This is total, right? What is P is what? So P is what actually is directly proportional to I, current, right? Where I is always greater than the threshold current. If you replace this one in the above part, we can write eta of t is equals to eta of external into I minus ith is nothing but the total output divided by the injected, that is I. If you divide separate I with I, so I gets cancelled, will become 1 ith by I, that is nothing but the factor. We are dividing with I, right? I is nothing but total number of injected electrons. How we got the previously like gth minus alpha bar, right? That same only we are assuming here as current parameters. So we are using that current parameters and we are able to find out the relation of that particular part. If for example, if your current is much greater than the threshold current, the eta t means total efficiency is equals to the eta of external. This means this one, external differential quantum efficiency, both will be equal. At what condition? At a condition when the current and threshold currents, if the current is much greater than the threshold current, means threshold current is very much less when we compare with the given current. If you had that kind of thing into the consideration, then both the things are equal. That means the total efficiency and the external quantum efficiency both will be the same one. There is no difference in that when we get this condition. Clear? So we should know that what condition we are assuming and at what value. We just want to write it down, that particular part. If you compare both the things into the consideration, if you see that one, how it is going to obtain by using this relation, we can able to obtain that particular equation as well. So that's how this current total efficiency is going to obtain. So we will substitute in this formula and we can find the efficiency, students. So till now what we discussed about its efficiency for the external, internal and total, right? All the efficiency of LEDs, how the LEDs efficiency is going to be used and what parameter the efficiency is going to obtain, and everything we have cleared. And next thing what we have to see in that particular equations would be its analysis part. That analysis, how we are going to see? We're going to see by using the formula. That means external power efficiency or device efficiency. What is the meaning of that? External, we are giving an external power towards it that can be used for the conversion of electrical input to the output, to the optical output. How do we obtain that? Basically, what is the power means? Power is nothing but voltage into current, right? So if you want to see the external power, if you want to find eta of EP, is nothing but output power is P by IV. IV is nothing but input power into 100. If you use that formula, we can able to substitute in the given conditions and we can able to write that one P by IV into 100%, because we want to find always efficiency in percentage, right? So we can substitute in the given condition and we can able to write it down in this formula. If you write those kind of thing, if you want to understand how it is going to work and what are the things it's going to depends, that can be used by using this relation. So what is the relation? Eta of EP is nothing but the electrical input to the output conversions. That will be considered to be the efficiency for the electrical input. What is the total efficiency? EP is equals to E theta. ET is nothing but total into EG. That is nothing but the energy gap by voltage into 100%. That also the things we can able to write by finding the external power efficiency of that particular device. Clear? So that device, how we are going to get that and what are the things the device is going to obtain, everything we can able to do it. Just we need to understand how it is going to work. If you know that how it is going to work and what are the things it's going to depends, we can easily obtain the given parameter analysis. Clear? So this thing also you have to note it down while we're discussing about it. Next part is about the same external power efficiency. That means how we going to get the Febvre-Perot laser diode. That is the one type of diode we do have, that is given by the Febvre-Perot. That is what is the use of this diode and how that this diode is going to work and all the things what is related to it, everything we are going to discuss in the next class. Okay, so this class, this is about what all we covered in today's session, students. We started from total efficiency, then external differential quantum efficiency. We talk about the relation of it, lasing action with a laser, and how the laser action is going to take place, what is the stage 1 and stage 2, how the lasing action is there, what is the population inversion, how the stimulate emission is going to take place, and basically what is the laser. So these all concepts we covered in our previous session as well, right? In today's sessions, the most important thing we have learned is efficiency. We started from laser, we started its working, we started this graph, we saw that particular graphs, analysis of the graph, working of the graph, and everything related to the all concepts we covered it. The thing what you need to understand is the lasing action. What is the laser is going to do the action and how the laser is going to work. that also we covered in our today's session. Then tomorrow's sessions we are going to learn in details about it. Then our concept related to the laser will be completed. So student, till now we have just covered all the topics, and let us see what are the things we just have to understand for that particular part of it, and what are the things is left out for us to understand in our laser concepts. That is on the sixth semester. Your just elective is there, so in that we just want to see the syllabus of it, how much is there for us to discuss all the things. I'm just going to tell you at the end. So that's the reason I'm just want to tell you should also be updated about your syllabus, right? We should know what are the things we have learning and what are the things still is there for us to learn. Everything we should know it. So in order to know everything, we should have to know about the syllabus of it, syllabus coverage, right? So how much is the syllabus is covered and how much is there. So here is there the syllabus of that particular subject. Let's see what is the left out coverage part is there. What else we do have to this learn it, and that is also we're going to see. IoT sensor. Next part, we're just going to see it's about the working, attenuation, dispersion. Yeah, this is the optical laser. So in this, what are the things we have learned in the third unit? We started the direct and indirect band energy gaps, right? Unit 3. And quantum efficiency, right? LED efficiency, we discuss. Modulation of LED, laser modes and threshold conditions, right? The next is rate and external quantum efficiency. Next, laser diode temperature effects, introduction of laser quantum laser amplifiers. This, if you learn it, the third unit will be completed. Then we are proceeding with the unit 4. Clear? So till now we have discussed about till these all concepts, starting from direct and indirect part of it, how the amplifiers and couplers will be going to use these energy parts and the structures, light source materials, quantum efficiency, LED powers and everything. Those we already covered, and we just have to see how it is going to work. That is also we going to see that. And we till now completed your external quantum efficiency, right? Even the external and the in external we have learned about that laser as well, right? How the laser efficiency is going to be used, and what are the things that the laser is going to work, and how it is going to approachable. What are the things that the laser should do it so that it can get the efficiency should be the part of consideration. So that is also we are going to cover. Next, what is left in the unit third is the power launching, coupling, lensing schemes, fiber to fiber joints, fiber spicing, and the temperature effects, introduction to the quantum laser, fiber amplifiers, how the fiber can be used as an amplifier, right? So what is basically the amplifier is all about? Amplifiers are the devices which is going to increase the strength of the signal, right? For that the reason we should know that how the laser is going to work for that as well. Those things we have just need to cover it. If you cover all the parameters in the laser, we need to proceed with the unit 4. Unit 4 is all about photo detectors and receivers. In photo detectors, we are going to see the derivation for it. How the SNR ratio, signal to noise ratio, can be used for different types of lasers, and what is the avalanche multiplication noise, comparison of photo detectors, fundamental receivers, operation pre-amplifier, error source, receiver configuration, probability of errors, quantum limit, and everything that will be going to cover in the fourth unit. And coming back to the unit fifth, it is about digital links and optical networks. So these are quite easy only links, we just have to learn it, and point to point link, how are we going to get that link, power, budget, and everything. So till now in unit 1, unit 2, unit 3, what we covered, unit 1 we have started from evolution of laser blocks and everything we covered. The wave guides also we see, the modes and fibers, how it is going to work, that is also we covered. In unit 2 we have learned about attenuation and dispersion, starting from losses of the signal and the material and distortion of waveguide, information capacity, determination, group delay and everything we have covered in unit 2. In unit 3 we started the reductors, right? Optical source amplifier and couplers. In that we have started its quantum efficiency, LED power, modulation also we have seen, mode and threshold condition, then rate equations we have seen just now, external quantum efficiency, this all we have covered. So next class I am going to explain you details of this. The same thing, you should also know that how is the part, what are the things that we are going to understand in that. So this is the part we have to left, we just left in the third unit. If you just completed this part, then we are proceeding with the fourth unit. Clear? So we have just in these parts we need to learn it. Then our third unit is going to be ended. Okay? So try to make the roads of running part. If you make the running notes, that only it will be easy for you to understand the further concepts. Okay? Take care. Have a great day. Goodbye.